So the differential equations that we've talked about, we're going to practice this technique of separation. And so it's a fairly generic, quick lesson for it, but this is about the extent that we will get to for differential equations. We'll look at one other idea, which is slope fields, and then after that we move on to area and volume. So just for these first couple, all we're going to do is take a look at how we could separate them. We're not actually going to integrate them. So we just want to see if you were given these equations, could you at least set it up to solve it by this technique of separation. So the key technique in this is that you have dy and some stuff equals dx and some stuff on that side. Right, so I'll let you guys work and see what you can come up with for those separations. But just separate them, don't solve them. Okay, so for the first one, I would probably set it up like this, so that when I want to separate them, I'll end up with 3y dy is negative x squared dx. In the next example, the only thing that really, there's not much of a challenge presented here, but we want to convert that to the other notation. So I get dy by dx equals cosine x over sine x. Whoops. So if I move these things around, dy equals cos x over sine x dx. And it might be handy, you could, as it is, it would work. It might also be handy to think of that as cotangent x dx. And then in the last one over here, I'm going to have this after I separate out the pieces from here. So if I was to rewrite this in that form, dx goes up to the top, the other x comes underneath, and that's where I'd be at if I was to start integrating these equations. So we'll actually try solving for some of these equations now, instead of just separating them. So I'll let you try on the first one. The first one is just going to be a general solution, which means there'll be a constant. That's what we mean when we say general solution, is you'll come up with a solution which we won't know what the constant is. It represents many possible answers. But in the second example here, what you're going to do is come up with the actual value, the single solution, using the information that the 0.13 is on the original graph. Okay. So my separation for the first one would be to take dy over y equal to x over x squared plus 4 dx. And then if I'm to integrate both sides, then what I'd like is, it would be good if I had a 2x there so that I could use some substitution, which means I would need to have a half out here. So I'll use u equal to x squared plus 4 du 2x dx. So now I can rewrite my integral, if that helps. Some of you might be at the stage where you no longer need to substitute, but just for this first example anyways, I'll use the substitution. So this would be the integral of 1 over y dy, and this will be 1/2 the integral 1 over u du. So if I was to integrate both sides here, this is going to be the natural log of y equals 1/2 the natural log of u. And of course, u is equal to x squared plus 4, so I'm going to have natural log y equals 1/2 the natural log x squared plus 4. And before I can, I definitely want to separate that y. I want to take it out of the natural log, but I can only do that when I have just two logs. This constant here needs to be dealt with. So I could rewrite this as 1/2 the natural log x squared plus 4, and this would be like natural log of e to the c. So e to a constant, that's just a constant. So you get this funny math still where you get natural log of a constant. So now I'm going to use the product rule to put them together, and I would get natural log, well, I might as well even go a step further while I'm doing it. I might as well take the 1/2 inside as well. So this will be natural log. And the square root can come inside as the multiplication by 1/2. So now, if natural log y equals this, I can drop the logs and I'd have natural log equals, I'd have y equals c x squared plus 4. So we'll just, that may need a bit of, is there any questions on that one? What I did with the constant may be the trickiest part. It's hard sometimes to work with the natural log. If you imagined we were in log base, I don't know, 2, and I had a constant, then the only way I could replace it, if I put 2 to the c, it would come in front as c log 2 of 2, which goes back to where I started. So that's what I did here when I replaced the constant. I replaced it in a clever way. And then e to the c is another constant. That's what happens in the next line where it disappeared. So that's what we mean when we ask for a general solution. There's a constant in the answer. But when we ask for the specific solution, here's I'll walk us through the first one and you can try the next one. In this example, what I'm going to do is it tells me that the slope is y over x squared. So basically we're being told that the derivative is equal to y over x squared. So I could rewrite this. I would get dy over y equals x to the negative 2 dx. And that's probably the most convenient way for me to write it so that I can take the integral on both sides. So for one of them, it's going to be the natural log of y. And on this side, if I do power rule, it's going to go -1 divide by -1. So it'll be -1 over x plus a constant. And again, we're going to rewrite this in exponential form so we can get y all by itself. I would end up with y equals e to the -1 over x plus a constant, which is going to be rewritten that way with the constant in the front. So the information I have is that I'm going to use this 0.13 to figure out the constant. That means y equals 3 and e equals 1. Sorry, x equals 1. I was writing the letter e. I just said the wrong thing. So this will be c would be equal to 3e. And I can put that back into my original, which was right here. So if I know what the constant is now, it's going to be y equals 3e, e to the -1 over x. And these have the same base, so most likely the way it would be written as the answer would be like this, adding a 1, because this is like e to the 1, and that rule of multiplying the common base and adding is there. Yeah. See ya. Okay, so that's probably the way it would be rewritten then before we were to see the final answer. So for the next question, I'll have you try and come up with the initial solution. Find the constant. They have a speech meet, I think. Yeah, speech meet. So here's the differential equation for you to work with. And here's the initial conditions that will give you what the constant was equal to. So see if you're able to decipher that. So I'm getting kind of crammed in here. I'm going to rewrite this on a different slide with you. So, oops, that's too small. Let me just expand that up. So I've got xy dx. And that's, let's see here. y squared minus 1. Let me just double check if I've written that out properly. Okay. So I'm going to move the dx to one side of the equation. So this is where I would probably start my separation. And now I'm going to move anything with an x to the right side, anything with a y to the left. So I've got y squared minus 1 over y. Oops, I forgot my dy here. dy equals negative x over e to the negative x squared dx. And at this point, I can't separate any further. And in our course, there won't be any other techniques for solving this kind of problem other than just to separate the variables. So it's time to integrate. There'll be a couple of things I can do to make these integrals a little easier to work with. Y minus 1 over y would make this side a little bit better to work with. And on the other side, if I put a half in front, I'll be able to put the negative 2x that I need so that I can use this as my function and then 2x as my derivative. Okay, so I'm on my way here. This will be y squared over 2 minus natural log y equals 1/2 the integral of du over e to the u. And that's going to give me well, sorry, it should be I'm going to rewrite the previous one just to make it a little easier to see. I'm going to rewrite, maybe I'll do 2 steps. I won't be lazy. Won't be lazy. So that's going to be the integral of e to the negative u du. Now let's see. So I just realized that this is going to work out, but we're going to have to do one more substitution. Up here, I should have done something. Can everybody see what I should have done before I moved forward so fast? Yeah, fair enough. But there's something here I could have done to make it, it'll still work if we keep going down this path, but yeah, I gotta, move it up to the top, right? There's a negative in there, so that would have saved me one last trouble, because here I'm going to have to then do one more substitution if I keep going. So I'll tough it out. So that means I need to put a negative here, so I can get a negative in there. And this will be y squared over 2. And I've got now e to the v dv. So that's going to be negative 1/2. So if I unwrap all this, I'll have to then replace it with negative 1/2 e to the negative u. That would then become negative 1/2 e to the, let's see here, negative x squared. So this would turn out to be 1/2 e to the x squared plus a constant. So I'll just write the final solution up there, but what we had was y squared over 2 minus natural log y equals 1/2 e to the x squared plus the constant. And the point that we were given was 0, 1. So if I substitute in x equals to 0, then this piece here is going to become a 1. And if I put in y equals 0, or sorry, y equals 1, this will be a 0. So I'll end up with 1/2 equals, yeah, there should have been that. 1/2 equals negative 1/2 plus the constant. So in this case, our constant would be equal to 1. So the specific solution that we would have gotten would look like that. Okay, so the last question will look similar here to what you did, with growth and decay. It says that the rate of change in the number of coyotes is directly proportional to 650 minus n. It says there are 300 initially, 2 years later there are 500. So I've given you one major hint here, that this clue, which states that directly proportional to that, would give you this hint. Okay, so that's what you're trying to figure out from that description. And you're going to get a model that looks, basically it's going to look something like, say there's, I don't know, the water source in their habitat only supports 650 coyotes, or something like that. Maybe there's only enough food for 650 coyotes. So that's the asymptote in this graph. There's going to be a 650 for an asymptote, and the population is going to be able to grow up until it skims and hits 650. So when you try to solve this differential equation, this is really what the model is going to look like when you're done, is roughly, if this is 650, the population is going to grow, but unfortunately, nature won't let it keep going. So at 650, it levels off. So you should be able to try and think about your solution and would it make sense compared to this model up here. Okay, so I'll let you try and work that out and come up with your equation. Okay, so I'm running out of space there. I'll do this one as well on a separate sheet, which was it's 650 minus n in the original if it's hard to read. So this is the equation that I'm trying to solve. So the change in population, the number of coyotes with respect to time, would be like this. So 650 minus n is equal to k dt. If I integrated both sides, I'm going to need to introduce a negative because of this thing here having a negative in front. So that means I'm going to have the negative natural log of 650 minus n equals kt plus a constant. And now I'm going to try to unravel this so I get an equation. So this is going to become the natural log of 650 minus n equals negative kt. And I know that's strange, but it's still plus a constant, even though the constant could be negative. So if I continue to work this out, I'm going to get e to the kt minus a constant is 650 coyotes minus the current population. So the end result is going to look like this. Put that in front. That should have been a plus. Yeah, it should have been a plus, sorry. So here's the model that would show the growth for that population. If you think about the way you'd be used to graphing, it would look like this. So you still have an asymptote of 650, and what you're now going to be doing is taking away some of that population. If your current value was, say, here, and here's the asymptote at 650, that's what's going to be decaying, is the gap between it. As the population grows, that gap keeps shrinking. So that's what's we're gonna find turns up there as the constant, is what's left over from the current population to 650. So we can figure that out by putting in the points. The first point is there's 300 coyotes when we start. Oops, sorry, C to. So that means there would be, let's see here, negative 350 is equal to negative C. So C equals 350. So 350 is the number of coyotes. If you want to make sense of what you just found, this is the number of coyotes that the population can grow by. So it should make sense that 350 is what's going to be changed by this continuous growth or decay, but in this case the population is growing. So if I finish up my model, I need to figure out what the growth, continuous growth rate is. So let me just take another look here. It says 2 years later there are 500. So 2 years later there's going to be 500 coyotes. So this will be enough to find the model that'll give us for this population, which is going to be negative 150 equals negative 350 e to the 2k, and that'll be, say, 15 out of 35 equals e to the 2k. So I get natural log, I can reduce that one more time here.
3 over 7.
Thank you. 3 over 7 equals 2k. So now I have my continuous growth, which is 3 out of 7 divided by 2, and I can then plug it back in to figure out what will they have. Let me just see here. After 3 years. So at 3 years, we'll have 650 take away the initial population, which has grown at this rate for 3 years. And we'll get, let's see here, 350, I'll plug this all into the calculator. 3 out of, oh sorry, that should have been a 7, not a 2. 3 out of 7 divided by 2 for 3 years. And means now there's going to be about 551.8. So we could say there'll be about 552 coyotes in that population.